We're going to try this. There we go. Okay. So really briefly, I started a long time ago working with computers, spent quite a bit of time with 8-bit and 16-bit and 36-bit, big, complicated machines. Worked for a company called Digital for a while and did applications and systems architecture, yada, yada, yada. Worked for a company called Oracle, worked on some database engines, performance, scalability, blah, blah, blah. And work for a company called SCI now, doing pretty much everything I've always done. So what I wanted to talk about today a little bit is some history, why we have arrived where we are today, where data is, what we call them disks, but it's really just persistent storage, right? The idea of a rotating chunk of rust is that's past. And we'll talk a little bit about databases from the standpoint of most computer stuff. I want to store some data and ideally sometime in the future get it back. And so that's the persistent storage idea. So you may recognize some of these pictures from your own careers or from history books or museums. You know, we've got punch cards and this little bottle, and I never actually experienced this, but that's a special magical glue so that you can put the little punch back in the hole. When it's easier to repair your computer program by fixing a missed punch, there was glue to do it. This device here was a 36,000 pound first commercial rotating magnetic media, leased by IBM. You could not buy one. They would be happy to let you use it.
It also had only one access store.
Oh yeah, no, this was, I mean, but it was magic at the time. At the time, this was magic. It revolutionized everything we know today. The old TS-11, the tape stretcher with the mechanical arms instead of the vacuum columns, which is not a picture of that. That's vacuum columns. Anyways, paper tapes. We all know how that worked. The concepts behind all these pieces of equipment are exactly what we use today.
One of the things that I found is that the guys at university, I'm training one up now, they don't have any concept of the way that sectors, heads, just that the concept is still there. So I think there's a definite teaching personally.
Oh, I mean, it's very easy to accuse the young people of today of being substandard to us, right? But that's true. I mean, and we'll get into that a little bit, but the punishment that we went through is one of the reasons I'm apparently very, very impatient. Like waiting for paper tape to get read through the thing, to me, it's just as painful as some, reading something out of non-volatile memory. So
paper tape is fun when you have the high-speed reader in the picture.
Yeah. Oh yeah. No, we've all been there. So the questions are, and the point of this wasted hour is, where's my data? Why is it there? And how long will it be there? And I wanted to point out, I mean, human beings have been doing data storage for a long time, persistently. Maybe not very fast, but durable. All right, so the big picture, the takeaway from all of this stuff is I/O is slow, memory is fast. That's the magic here. That's what all of this is about. We spend billions of dollars developing technology because of that. So, perspective. If a memory access were to take 1 second, going out to disk is going to take a week. And that's kind of the order of magnitude to be thinking about every time you do a disk I/O in your database or your application, whatever it is. That's the order of magnitude. Justify every I/O you do. Avoid it any way you can. So current technology, DDR4, we're talking 10 nanoseconds. let's just call it instant, right? I mean, it costs nothing, right? Why worry about it? A solids or a rotating media, 500,000 times slower. So to improve application performance, I go to a customer site, whatever, to get a 10% performance improvement isn't difficult. I just need to avoid one IO. The farther away the data is from my computer program, the worse my life is. Plain and simple. Keep data close to home. Don't do an IO unless you have a choice. If there's no other way to accomplish the task, go ahead and do the IO. But I don't want to hear about people doing extra IOs. Don't do them. The end result of all of this is average CPU consumption or consumption rate will increase. That's my goal. When I go to talk to a customer who's having a performance problem, if they have a lot of work to do, I want to see their CPU consumption go up, because then I know we're waiting less. And many people get very annoyed by this because they want to see, 30% CPU consumption, we got lots of headroom. And also your application is slow at the same time. So you bought this expensive computer and you're only willing to use a third of it. So where might data be? Okay, it's going to be on a stone tablet somewhere. Well, that's the device. That's some rust that's spinning on a little platter. It might be in my storage controller. It might be inside my operating system. It might be a cache in my database engine, whether it's RMS or RDB or Oracle, whatever, or it might be in my application. Really no great way to know ahead of time where you're going to find it. And I say, or in reality, it's going to be in all of those places. My customer record or my sales invoice or whatever is going to be replicated all over the place. And people get very excited talking about, security, data at risk, and data at rest has to be encrypted and all this nonsense. It's BS, okay? Because it's all over the place. You just don't have any way of knowing. Interconnect speed. So my sales guy works for some big fancy company that sells some big expensive storage controller and takes my CIO or my CTO out to lunch and they have champagne or whatever it is that they do and tells the guy, my storage controller is the best. It's the fastest. We sub-microsecond this, blah, 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 RAM and NVMe and batteries and stuff. And I'm going to connect it to your computer over a piece of wire in potentially the same room, maybe the same building, maybe in the cloud. So any advantage of sub-microsecond, yada, 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 is completely eliminated by the speed of light. So the transfer rate that the storage vendor will give you is just a promise that it's never going to go faster than that. But in reality, you'll never get marketing latency or marketing transfer rates. And so we play the game. Be very, very conscious when you're communicating about the difference between bits per second and bytes per second. And as an order of approximation, the difference is 10 times. So it's very easy for the sales guy to convince your manager that a bigger number is better number. It may not be, may make no difference. Even if my storage controller, my RAM device, my NV, whatever it is, if its latency was truly zero, okay, it's not going to make any difference because, especially on an operating system, when you do an IO, there's massive amounts of overhead necessary to do an IO. Locking of data pages and this and that and the other thing is kind of sort of taken into account here. The machinery in a device driver, the machinery in setting up for an AST to be delivered and process scheduling and AST, like all of that stuff counts. So if the IO cost nothing, the time is very, very measurable. And if you do look at your T4 data and you see interrupt stack at, whatever it is, 30%, 70%, whatever, that's the punishment. That's the cost of doing an IO. So avoid, even though your boss spent $1 million and bought you this fancy storage controller with write back cache and blah, 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 don't do an IO. If you're going to have to communicate with another computer, think long and hard. Is this really truly necessary? Because that's an IO.
And when you do, make it count.
Yeah.
Don't read one block, read 100.
No, you're 100%
Your
right.
comment about CPU utilization applies to interrupt stack also.
Mhm.
The more efficient, the more volume you're ramming through, the higher interrupt stack will be. So low interrupt stack is not necessarily a good thing.
Well, yeah. Use jumbo frames.
Yeah.
Been around for a long time. I've yet to visit a customer when I arrive where jumbo frames are enabled. No, hasn't been happening. Been there forever. Now, does it work with DECnet? Well, that's arguable. But so caches at a high level, you have a read cache where data is deposited. When I go back and look, I'll find it in some repository somewhere along that long continuum. Write caches are a place where I can deposit data and keep going. And sometime in the future, that data will make its way to persistent media. They show up all over the place. We've got disk drives with write-back caches. We have storage controllers with write-back caches. We have operating systems with write-back caches. So be aware of, especially write caches, right? I mean, VMS is punishingly slow because everybody does write-through caching, right? We don't do write-back in general. And so we pay the penalty. Linux looks fast, Windows looks fast. They don't necessarily write the data back to disk, even though your IO is done. All right, for those of us still using this ancient technology, just to give you an idea, 2 milliseconds rotation latency on average. The firmware, all this, the operating system in each disk drive plays some clever games where it figures out where the media is and can get the heads there. It'll read the second half of your data as it passes the heads, and then reads the first half of the data when it comes back around again, puts together in the buffer to try to make things a little more optimized. Onboard caches, they're tiny, but they're effective. Turn on, for me, because I'm a performance guy, turn on the write-back cache in your SCSI disk, unless you're a bank, but otherwise just turn it on. And your disks become much, much, much faster, apparently. And here's a little example that I cobbled together with, I don't know who wrote SCSI mode. I'm guessing it was a Steve Hoffman kind of thing. But anyways, it's got an awful interface. And you can poke the bits inside of the firmware inside of the device, and it becomes faster. But as I mentioned before, we don't use rotating media anymore. Doesn't exist. All your cloud providers and stuff like that, there's no rotating media in that data center. It's all solid state storage. Why? Because these things fail constantly. They have unpredictable and unreliable performance. And all of the cloud vendors want to offer you their salesperson to tell you that they are the fastest. And the only way they're the fastest is to do what everybody else does. There's no magic here. The technologies, couple different things. There's some backplane devices that communicate in one protocol or another, this and that. In your storage controllers, your big 3PAR, what's the new thing, Electra. Keep in mind that a write is almost always faster than a read, because as soon as the storage controller gets the data, it says we're done. If you have to read data that's not in somebody's cache and it has to go all the way out to some memory chip somewhere, it's slower. So write your application so you only write data. Never read it, because reading is slower. That also, that little paradigm there means that I can write an infinitely fast database engine, because you promise never to read the data back. So, all right, so your modern storage controller that the sales guy is going to sell your department is a extremely complicated piece of equipment. The operating system here is probably bigger than VMS for all I know. I mean, it does lots and lots of stuff. There's many CPUs, there's many HBAs and network. It's a big, complicated piece of equipment. What's a characteristic of a big, complicated piece of equipment that's built by a human being? It's got bugs, guaranteed. You may never see them, but yeah, I wouldn't trust my data in one of these if I had to. The cache sizes in these, if there is rotating media, are massive, terabytes, because writing to disk is so slow. Reading from disk is so slow. The data is protected with multiple different kinds of redundant technologies, battery backups, and yada, 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 yada. So you're putting a lot of trust in the people that write the software and design this hardware. So I've showed this picture before. It's been around forever, but this is pictorially all of the different kinds of redundant data protection technologies that have been developed since the, let's just say, late 70s, probably. Operating systems. So now we're up in the DMS, Linux, Windows. They're all the same. Okay, we've got different names for things. The interfaces are different. Some of them have a nice GUI. Some of them have a GUI nice. Some of them don't have a GUI at all. But they all do the same thing, right? There's caches in the operating system where we read, for example, file headers, okay, or directories. And we just keep them in a special place in memory so access is faster later. We keep the contents of your files in memory somewhere, so that if you go back and reread data, or if you have shown that you're going to read block 100, block 200, block 300, block 400, the operating system eventually will say, I wonder if they're going to read block 500, and we'll do it ahead for you. So all of those things happen. Database engines, whether it's SQL Server, Oracle, or RDB, or whatever, they're all the same, right? They try very, very hard not to write to disk while you're waiting. They try very, very hard to follow those ACID properties where if I commit my transaction, I'm guaranteed to get my data back later, is the promise. Now, it's always not true in the history of time, but still. And so, and then up in my application, maybe I have a little hash table or a little queue of things that I know there's only 50 states and they don't change very often. So I've got a little optimization in my application where I have a hash table which converts the state code to the name of the state, whatever. So these are all the different places inside of my computer where my data might be and how I'm avoiding talking to those expensive, slow disks. So the philosophical question of write back caching boils down to the real question of RTO and RPO, right? How much data am I willing to lose? For some businesses, well, actually, for every business, the IT manager says, oh, zero. We can't afford to lose any information at all about the amount of sand at my gravel yard in bin number 7. So then the storage vendor says, well, for $1 million, I can guarantee that zero data loss. Then all of a sudden, data loss becomes an acceptable conversation. Because for $100, I can guarantee you that you will have all of your data except for the last 10 seconds. I can't guarantee that. Now, there's a solution. I don't need $1 million. I can do it for $100. So be aware. I mean, yes, the purist wants everything to look lovely, but in reality, there's a cost to this. It's in either performance or it's in dollars. What we do in database world is I'm going to insert 100 records into my database, whatever, the sales data, the customer update, balances, whatever it is, data. To make it look fast, when I commit my transaction, I'm going to do one IO. One single write to a journal, the redo log, depending on the technology and the terminology you're used to. So even though I've done a lot of complicated work, I do one IO to disk. And that's going to take however long it takes, a millisecond, 10 milliseconds, whatever it is, X. That's how we play games with write back caching. The data isn't in your database yet. It's still in memory somewhere. It's not in the big pool of the files, but it's on disk in a journal. So that's the kind of games that we play to avoid having to write to disk. And we still, with a wink and a nod, promise zero data loss. On OpenVMS, we're all familiar with the XFC cache. Great thing, wonderful. It solved, was it version 5 when XFC came out? Whenever it was. It solved a bunch of performance problems for a lot of people.
Just later than 5.
Is it?
The IOC before.
Yeah, VIOC was first. Maybe it was 7. Probably 7. Well,
it's late. It's more recent.
XFC cache is wonderful. It is a write-through read cache. Okay, so it's not going to help any of your write IO performance. It's going to make it worse, measurably. Because we use that expensive CPU to drag data from your buffer into the XFC cache. And then we're actually going to write it to disk. So it's going to get drugged from the buffer onto the HBA, the virtual HBA. Some device driver is going to get it. It's going to get drugged back across the bus again to go where it's going to go. This penalty is significant. So, and significant, I'm saying, I'll make up a number, 10%. So for files that you know that you're not going to read again soon, and the easy example is every day I back up my whatever it is to a save set on disk because I want to be able to restore it tomorrow, whatever. Put that save set in a directory marked no cache. And I've measured 10% performance improvement for free. Costs me nothing. What is the difference? I'm not putting that data into the XFC cache, throwing out other useful data along the way to make room. And I know that I'm not going to read this file again. I haven't needed my backup for the last 4 years. So why punish everybody else in the system? So yeah, it does need a little guidance. It needs a hint sometimes. If I'm in a cluster, which is the solution to the world's problems, according to some people, oh, you got to use clusters. Clusters are outrageously slow. The overhead of running in a cluster is massive all over the place, not just for certain things. One of them is if I have my RMS index file that's the master data for my customer list or whatever it is that I do, that file doesn't get cached in the XFC cache 99.9% of the time because everybody opens their index files for read-write access because they want to modify their customer data. Be aware of that. I mean, we've got solutions for that characteristic, but XFC isn't a solution to everything. By default, it's 50% of the memory of my computer maximum size. So if I have a modern 96 gig machine or whatever it is that we buy, 48 gig is going to be the maximum size of the XFC cache. a simple, easy thing that I can do when I show up at a customer site is nobody calls me if they're happy, right? They're already in pain. They've already got a problem. So I show up, look at the problem, figure out what it is that they do. Their problems are always IO, right? I mean, at the end of the day, the computer's waiting for something. It's waiting for some storage controller. And so I say, well, why don't we increase the size of your machine from whatever, 128 gig to 256 gig. And then I make the XFC minimum and maximum cache size be 128 plus 64. So the entire rest of the operating system and your programs and everything still get the same 64 gig of memory that you were using before. And now my XFC cache is really big. It's also fast. We'll talk a little bit about what faster means. Blah, 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 blah. Okay. So I want a high-speed XFC cache. Remember, all modern computers use, there's a whole nother presentation about this, but in summary, all modern computers have a little cache inside the CPU chip of page table entries or some derivation of that name that I need to reference. For every memory reference that I do in my program, I need to look at this page table entry to see if I have access to that piece of virtual memory. Okay, that's where the protection comes from, the 4 levels of the onion and all these things. By using these, depending on the operating system and the architecture of the computer, these huge pages, large pages, whatever it is, VMS would call granularity hints back in the alpha days. I can have one page table entry map 4 gigabytes or 128 gigabytes of memory in one page table entry. And so by having bigger pages, I have less translation buffer cache misses, and we gain performance. I mean, I benchmarked at Oracle some application workloads that were entirely fake. And to prove that, yes, this mattered. Now, your application will never get that level of benefit, but still, take advantage of this. Don't be afraid of memory. Lock your XFC cache in memory. On alpha emulators, I doubt this makes a measurable difference, but on real hardware, x86 as well as integrity, this matters. So here's how you do it. I will give you the caveat that no good deed goes unpunished, and you can absolutely burn yourself by making a typo here. An extra 0 will make your next reboot an awful lot more painful.
More exciting.
More exciting, yes. Add interest to your afternoon. So when to avoid the XFC cache, as I mentioned, if you suspect you're not going to read the data again, the backup save sets is the easy example. Do this.
That was exactly the comment I was going to make. Get back up save sets and a regular directory, you stash them in directory with no cache set.
Yeah.
Because it's effectively over reasonable times.
Yep. Yeah, I mean, there's no point in wasting the CPU time and throwing everybody else's data out of the cache for something that's useless. So here's how we look to see how the XFC cache is working. The primitive, novice user, show memory / cache, look at the files that are most actively accessed on your system disk. And what you're going to see, I don't know if I showed this in this example. Back in the olden days, when we were writing operating system and application programs on VAX, it was pounded into our heads. Do not have non-zero private data in your shareable image. Okay, and so everything's got to be a demand 0 section. Apparently that was long ago lost, and for most systems, on the system disk, it's going to be DEXC share or librtl are the #1 files on the computer of XFC of IO. Now it all gets absorbed in the XFC cache, but it was still an IO nonetheless. If you want to dig a little deeper and be an adult here in the room, play with the XFC extension to SDA. Show cache, show brief. What I use this for is it calculates for me accurately how long IOs take. Everything else is 2 decimal digits of a second, which is 0 in the real world. But these are real numbers. So that's a hint that you can play with to show off your skills with both SDA as well as talking to the storage vendor. Well, sure, your storage controller is expensive, but it takes a long, long time to get an IO to it and then to wait for the response. RMS, my good friend Hein Venenheuvel will bore you to death in an entertaining fashion about all the ways you can make RMS faster and avoid your CIDRs and all this nonsense. Look, we want to do less IO. If we have the same amount of data, we want to do bigger IO. And so we also don't want to do an IO if we don't have to. So these characteristics, parameters, switches, whatever you want to call it, and the defaults on VMS were probably inappropriate in 1982. They're certainly inappropriate today. And in fact, one of the challenges that we have is that the VMS device drivers and the whole infrastructure, I mean, I'm not bad-mouthing anybody here, but IOs are tiny. 256 blocks on a 16 gig HBA is embarrassing. I mean, every other operating system in the world will do gigabytes of IOs across this piece of fiber. But maximize what you can. Do not be afraid. I go to a customer site, they use the default value of 3 or whatever the heck it is. And it's like, let's make it 127. And they say, oh, wow, that's a big change. Why don't we go, should we go to like 9 first? Or maybe let's just double it and go to 6. I was like, what? So anyways, do bigger IOs, put them off as long as you can with the deferred write or the right back, right behind, whatever it is. If you can't do right behind or deferred write, fine. At least you've tried. Maybe your application, you've got a lot of contention for buckets or whatever, and it's really not helping you. At least you tried. Give it a stab. Larger buckets are better in all cases, except when they're not. There are some boundaries with contention and stuff like that. But again, at least you've tried. The optimized locking protocols, when you have global buffers, save your bacon. That's a gimme. If you have an index file that's opened by multiple people for write access, especially if you've chosen to use clusters, global buffers help. There's no downside for all intent and purposes. A couple bytes of memory. Keep the data close to your option or your application. We talked about a little hash table. I helped a customer recently who their 1980s technology, somebody went to the class that said all data should be normalized as much as possible, and they keep a description of the menus, like it's a green screen application, it's got all these menus and stuff. They keep the definition of all those in the database. And so I'm on the main customer service menu or whatever it is, and I select, look up customer. So the application asks the database engine, well, what does the next menu look like? And so it comes back with a bunch of data, and here's all the columns, and here's where they are on the screen, and the locations, all that stuff. And they tab over to the, enter customer ID field or whatever. So the application does a database lookup. How is this screen drawn? So to do anything at all, you've done a dozen transactions, and you've got a whole bunch of very efficient, customer relationship people on the computer. And so the database is doing hundreds of transactions a second that accomplish nothing. because they keep reading the same data over and over again as they traverse these menus. So I just wrote them a tiny little bit of code that puts all of the data in a hash table the first time you look up that menu. Completely transparent to the entire rest of the enterprise. And their transaction rate goes from, whatever it was to nothing. And what's left is the actual transactions of running the business. So keep the data close to the application. Don't trust the database engine because they're big and ugly and expensive. Global buffers, if you haven't, and I know everybody in this room has, but if you haven't, sysuaf is the gimme and rights list, depending on your VMS version. Set it to 5%. I don't know what the right number of global buffers is, truly, but it's not 0. So 5% for fun, because we're computer geeks, turn on statistics collection, and then you can use monitor RMS, and it will tell you the number of record fetches and bucket hits and also locking operations or whatever in real time. It's fun. Costs you nothing. As with everything in computers, it's a compromise, right? Nothing is free. So there's a couple sysgen parameters that might be impacted. Fortunately, the least important ones are dynamic. The most important one is unfortunately static, and you got to reboot. Make it big. If the default is 2,500, whatever it is, and you need more, go to 5,000. Don't say, oh, I need 10 more global sections, so I'm going to make it 2510. Go to 5,000. It costs you nothing until you need to increase it again, and then it's cost you a downtime. All right, so you've seen Hein's presentations, you've listened to mine. Oh, global buffer is just going to solve all my world's problems, and gosh, this is the most important file in my entire system. So I'm going to global buffer at 100% because I want to, make really sure that. So a little secret is when you open the file, RMS has to map that global section, and that involves going through and creating all these little page table entries to my process address space, and that's really expensive. And so show up at a customer site, and MMG Spinlock is punishing them. Get looking a little deeper, and nothing makes sense. I mean, their application's super simple. Well, what was happening was they were calling the rights, what was it? They were changing personas. Like every time they went to the application, they changed to a different persona, which caused VMS to re-access rightslist.dat because you have to read your identifiers over and over and over and over and over again. They had probably followed my advice, turned on a whole bunch of global buffers on their rights list file, and they got a gajillion users in their system. So rights list was really big. So the biggest punishment in the entire system was all of this locking and mapping the file, and then they'd read the identifiers, and each one of those got a bucket lock as well as a record. It was a junk show. So what I did here was and this is disallowed. I'll say you right up front. HP VSI legitimately could take me to court because I'm not allowed to reverse engineer any of the software in the operating system. That's part of the T's and the C's. So of course that's what I did. And I modified sys $get UAI or whatever the heck it is to patch the Itanium instruction to set the no query locking bit. And so now all the record locking goes away. The MMG is still there, but I've eliminated all of the locking operations. Then I went back to my good friend, probably Styles. Anyways, somebody at VSI, and I guilted them into making that change. And so you get that benefit. But that was a fun, constantly opening and closing the file and rereading a little chunk of rights list. Multi-block count and multi-buffer count How are we doing on time here? I got 5 minutes. All right, we'll be done. 255 blocks is tiny, but it's also the maximum. So set it. I mean,
Also enough.
don't be afraid. It's often enough. It's certainly better than less, except when it's not. So I tried to be a really good citizen of the world and set multi-block count to 255 for an application which writes a little bit of data and then does a flush. So before it would write 2 or 3 blocks at a time. Now it's writing 256 blocks at a time. Lesson learned. For sequential files, which is what most people end up doing most of the time, right? You write a report, you read a big file, you search a big file, whatever it is, just set them big. The queue depth, pick a number, 4, 8, 16, 2, whatever, just more than 0. I've recently been working at a customer site with big expensive computers, and they bought all the stuff that the salesperson told them to buy. And for them, 32 was about the right queue depth for maximum throughput. For other sites, it's less. What else to say about that? Nothing really. Right behind, yeah, keep dirty buffers in memory as long as you can stand it. Really boils down to RTO and RPO. Another site recently was they have a log file that sort of the debug log file of what the application's doing. Many years ago, somebody decided that it was really important that the log be accurate and current, which it really doesn't. And so they have flush all over the place. And so I told them, why don't you do it once a minute? I mean, for lack of a better idea, just do it. We also have ways to cause everybody else in the cluster to write their deferred buffers to index files back. And Hein Van and Heuvel's shared a little program, which I'll give to you or have you go to him to do it. Monitor RMS, we talked about, see what it's doing. RDB databases, I talked about a lot. There's all sorts of caching and buffering that goes on to keep from writing data to disk. If you happen to be unfortunate enough to use one of these database engines, come see me afterwards. Blah, 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 blah. Oracle's SQL Server, Postgres, I mean, they're all the same, right? Try to avoid writing right to the redo or the journal log, whatever you call it. Use large pages as much as you can. Cares about that. Same thing. This was a very brief, probably my last little story. Customer site, financial trading, stock exchange kind of place. End of day processing, they have to sort of rewind to the system to get ready for tomorrow. Like they've cleaned up everything we did today and we need to rewind for tomorrow. They use their own very sophisticated journaling mechanism, and they have files that are initialized to all zeros, and they can write data. And so end of day processing, they have to reset that file back to empty. And they don't really have a great way of doing big IOs, right? This is optimized for the fastest possible single block synchronous IO. And this was taking, I don't know, an hour and a half, hour and a quarter. Overnight, as the business got bigger and bigger and bigger, this time got longer and longer and longer. The nighttime stayed the same amount of time, so they needed to get more done. And so we made a 4-line change to their command procedure. So at the beginning of the operation, we use a big copy command to copy this data into a DECRAM device. We run the initialization, and then we copy it back. And I was severely punished for that because the overnight crew used this 90 minutes to go out and get a smoke and a coffee. And so we took it from an hour and a half or whatever, hour and a quarter to 2 minutes. And they thought I had broken it. They were very upset. And we assured them that no, in fact, this is how it is now, and you've lost your break time. And it was a big deal. I mean, like, truly. They probably haven't forgiven me. All right. Does anybody use NFS? Okay, the answer is not so much. The protocol NFS version 3 anyhow, which we're saddled with today, isn't all that wonderful. And about the best I can do is ask the server not to write this data to disk. Sorry. Oh yeah, jumbo frames helps a lot here. Nobody uses it on VMS. Talked about that. So for fun, I do this every year. I can buy a 7 terabyte SSD, 12 gigabytes a second. So, modern SAS technology for $1,200 delivered before noon tomorrow. Now, VMS people, how useful is a 7 terabyte SAS disk plugged into the side of my computer? It's not, because my volume limit is 2 terabytes. So you have to buy a whole bunch of 2 terabyte volumes but anyway, that's pretty impressive that this is a commodity device that I can buy on Amazon. A little chart for your reference. The only ones you care about are 8 and 16. You only care about 16 if you're on a 2800 i6 or whatever it is, or some modern x86, and then you can probably get much, much better. In your x86 hosts, put NVMe in it. Spend the money. Nothing will be faster. You'll look like a hero. All right. How'd they do on time? Yes.